Welcome to ExplaQuiz channel. In this video, we are going to understand convolutional neural networks or CNNs and see why they are so powerful for image-related tasks. We will go step by step through the architecture, the main layers, and a real CNN design example, and quizzes along the way will test your understanding. A convolutional neural network is specially designed for data arranged like a grid, and the best example is an image. An image is basically a matrix of pixels where each pixel stores numerical values representing brightness and color. Because the data is organized spatially, nearby pixels often carry related information. That is exactly why CNNs are so effective for visual tasks. CNNs are inspired by the way the visual system in the brain works. In biological vision, each neuron responds to a limited region called a receptive field, and CNN neurons do something very similar. Early layers usually notice simple patterns like edges and curves, while deeper layers combine them into shapes, faces, or objects. In a very real sense, CNNs help give computers a form of sight. A typical CNN is built from three major parts: convolution layers, pooling layers, and fully connected layers. The convolution part extracts patterns from the image, the pooling part compresses the representation, and the fully connected part uses those learned features for prediction. You can think of it as feature extraction first, decision-making later. This overall flow forms the backbone of most CNN models. The convolution layer is the heart of a CNN. Here, a small matrix called a kernel or filter moves across the image and performs a dot product with local pixel regions. As it slides, it creates a new 2D output called an activation map, which tells us where that feature appears strongly. The step size of this movement is called stride, and it affects the output size. Now that we've covered CNN basics, let's test what we've learned so far. Here's quiz number 1. See if you can get it right. Question 1. Why are CNNs especially suitable for images? The correct answer is, images are grid-like pixel data. CNNs are designed for grid-structured data, and images are made of pixels arranged in a grid. This lets the network detect local spatial patterns efficiently. Question 2. What is a receptive field in a CNN? The correct answer is a local region seen by a neuron. A receptive field is the limited area of input that a neuron responds to. This local focus is one of the key ideas behind CNNs. Question 3. What does the convolution operation produce as it slides over the image? The correct answer is an activation map. As the kernel moves across the image, it computes responses at different positions. These responses together form the activation map. Convolution is powerful because it uses sparse interaction, parameter sharing, and equivariance to translation. Sparse interaction means each output depends only on a small local patch, so the model needs fewer parameters. Parameter sharing means the same kernel weights are reused across the image, which is both memory efficient and logically sensible. Because of this, if an object shifts in the image, the feature map shifts in a corresponding way too. After convolution, CNNs often use pooling to reduce the spatial size of the representation. Instead of keeping every value, pooling summarizes a small neighborhood, and max pooling usually keeps the highest value. This cuts down computation and also makes the network less sensitive to small shifts in object position. So pooling helps the model become more compact and more robust. The fully connected layer comes near the end of the network. Here neurons are connected in the usual dense way, just like in a standard neural network. Its job is to take the extracted features and convert them into the final output, such as class probabilities. So once convolution and pooling have done the feature learning, the fully connected layer handles the final decision. Convolution by itself is a linear operation, but images and visual patterns are not purely linear, so CNNs need nonlinearity. Sigmoid and Tun were popular earlier, but both can saturate and slow learning. ReLU, which simply keeps positive values and clips negatives to zero, became very popular because it trains faster and works reliably in many cases. With a proper learning rate, ReLU is usually the practical choice, so that covers the key working parts of a CNN layer stack. Now that we've covered CNN layers, let's test what we've learned so far. Here's quiz number 2. See if you can get it right. Question 1. Which idea allows the same filter weights to be reused across the image? The correct answer is parameter sharing. Parameter sharing means one kernel uses the same weights at every spatial location. This greatly reduces the number of learnable parameters. Question 2. What is the most common pooling method mentioned in the article? The correct answer is max pooling. Max pooling keeps the maximum value from a local neighborhood. It is the most commonly used pooling operation in CNNs. Question 3. Why is ReLU often preferred over sigmoid and Thun? The correct answer is it accelerates convergence significantly. The article notes that ReLU is more reliable and can speed up convergence compared with sigmoid and Thun. That makes it a very practical activation function. Now let us look at a practical CNN design. The article uses the Fashion MNIST dataset, which contains 28 by 28 grayscale clothing images across 10 classes. The architecture follows a clean pattern: convolution, batch normalization, ReLU, pooling, then another similar block, and finally a fully connected layer. This is a very common and sensible CNN design for beginner-level image classification. In the first convolution layer, the model uses 5 by 5 kernels, stride 1, and padding 2. Because of that padding, the spatial size remains 28 by 28, while the depth becomes 16 feature maps. Then max pooling with a 2 by 2 filter and stride 2 cuts the width and height in half. So after the first conv and pool block, the representation becomes 14 by 14 by 16. The second convolution layer again uses 5 by 5 kernels, stride 1 and padding 2, so the spatial size stays 14 by 14. This time the number of filters increases, giving an output depth of 32. After the second max pooling step, the feature maps shrink to 7 by 7 by 32. At this stage, the model has a compact but rich representation of the image. The network also uses batch normalization, which helps training remain stable and reduces sensitivity to poor initialization. It was trained using cross-entropy loss and the Adam optimizer with a learning rate of 0.001, reaching 90% accuracy on the test set. Beyond this example, CNNs are widely used in object detection, semantic segmentation and image captioning. So now we have completed the full journey from CNN basics to a working architecture and real applications. Now that we've covered CNN design example, let's test what we've learned so far. Here's quiz number 3. See if you can get it right. Question 1. Which dataset was used in the CNN design example? The correct answer is Fashion MNIST clothing dataset. The article specifically uses Fashion MNIST, a dataset of grayscale clothing images with 10 classes. It is a common benchmark for image classification. Question 2. After the first pooling layer, what is the output size? The correct answer is 14 by 14 by 16. The first convolution keeps the image at 28 by 28 with depth 16, and the first pooling layer halves the spatial dimensions. That gives 14 by 14 by 16. Question 3. What test accuracy did the model achieve after training? The correct answer is 90%. The article states that the trained CNN reached 90% accuracy on the test dataset. This shows the architecture performed quite well. Today you learned how CNNs detect visual patterns, compress information, and finally classify images using learned features. Hopefully you also checked your understanding with the quizzes and saw which concepts are already clear for you. If you enjoyed this format, do like, share and subscribe to ExplaQuiz channel for more interactive learning videos.